Okay, we continue a little bit more, looking at some of these examples. For the rotational channel, you see some measurements, some of the velocity profiles at different locations, and you have here the rotating channel and then the pressure side. So here you see the mean velocity at different locations, and you see it becomes more and more sharp, this shoulder. So clearly more and more turbulent. While on a suction side, the opposite happens. It becomes more and more laminar. The velocity increases and it tends more and more towards the laminar parabola. For the turbulent intensities, that is the fluctuation squared. In a turbulent flow, they peak normally very close to a wall, very close indeed, and then goes to zero on the wall itself. So here you are on the turbulent side, the unstable side. So then this region where you have very high turbulent activity is sort of squeezed more and more towards the wall. While on the suction side, you see they are getting more and more laminar, tending more and more towards zero. So less and less turbulent activity. The damping here is quite strong. So this is measurements, and if you try to simulate this then with a K epsilon, you wouldn't see a difference. He will give you exactly the same on each side, which is clearly wrong. Of course, you can find K epsilon models, K omega models that has some additional terms, including trying to take into account these rotational effects. So yes, they exist, but you have to be aware of them. Here it's the skin friction velocity on the two different sides of a rotating channel. And this is some measurements done by Johnston in the mid-70s. So on the pressure side, you increase the turbulence, higher and higher friction forces. While on the suction side, lower turbulent activity, you reduce the turbulent activity, you reduce the friction. These points down here, they are not to be believed. We actually talked to Johnston and he admitted that these points here were highly questionable. And also this should be non-dimensionalized, so the sum of the forces should be zero. Then the friction forces should add together to 1. So this is actually not possible to achieve. But the stronger and stronger rotation, the stronger and stronger this effect will be, yes. So he will tend towards laminar here. Then it was hard for him to measure correctly. Another popular test case, sudden expansion, backward facing step. And this is also a classical problem for a standard K epsilon model. If you play around with this problem here, finding this reattachment point for different Reynolds number, then you can get any result you like actually by just playing around with the measures. How well you resolve the boundary layer here, you will get a different answer every time if you use the K epsilon model. Very bad model for this problem. I think they have some results here using, they have simulated here with using the K epsilon, and then they have switched on the ASM model. So, well here, yeah, this was experiments actually. But here you have some simulations. BVM, that should be the K epsilon model, and then the algebraic stress model. And the ASM model, he can find the solution fairly decently. The K epsilon, no, he is not. It's not so nice. You see clearly here, looking at the different turbulent intensities, different Reynolds stresses. Well, of course, then the K epsilon will have an impossible job to describing those accurately, of course. You find on this lecture notes in turbulence modeling, you find several of these examples as well. So, velocity profile in a wake behind a flat plate, expansion, and well, a lot of different problems there. You have a nice summing up here for the different models, advantages, disadvantages, and the K epsilon down here. And as it says here, currently the most popular two-equation model, and it still is. And the reason is, I think, mostly historical. It was the first two-equation model that was successful, and since then everybody started to use it. So it has a lot of testing, and you find for any problem you will find some results in the industry where people have tried it with K epsilon. So it's fairly easy to choose it, but sadly it's definitely not the best one. Especially for some particular cases, then you should have used the K omega instead, for instance. But everybody's using sort of K epsilon without thinking, and that's a bad idea. So to sum up, the two-equation models, they fit fairly well when you have boundary layers, jets alongside the plane wall, wakes, mixing layers, plumes, tubes, channels, whatever, and several 3D flows, unless you have some really strong vorticity, chemical reactions, that's really messy. Some buoyancy-driven flows, yes, it's also possible. What they don't like convex, concave walls. They really don't like it. Strongly swirling, strong recirculation zones. They don't like it at all. Rotating flows, of course. Multi-phase, stratified flows, and also when things becomes laminar in different zones, then also they have a tendency to fail. There typically you need to switch on some low Reynolds number models to handle laminar tendency inside your domain. Yeah, I won't go through all this. Let us start by looking into some of these articles that has been sort of provided as examples. Here we have a rotational channel, and the problem is a backward facing step like this. We have one large circulation zone here, finding this reattachment point as typically the classical problem. But here also we have started rotation for the entire channel. So you have zero rotation, positive rotation, and negative rotation. So that's the three different cases we are looking at in this article. And to do the simulation, you have K epsilon, and you have then also switched on the algebraic stress model. And here you see then a list of the different constants that are involved in an algebraic stress model. Will of course differ depending on what model you choose, but you see it's not so easy anymore to just choose a couple of constants like in the K epsilon. So they can be pretty complex. Let's see if we can find the equation system. Something like this. The mean velocity here for the continuity and the Navier-Stokes. And here, yes, we have the Reynolds stresses, and also here you'll have a Coriolis force, then sort of an external force, since we are looking at it in a rotational frame. So the ASM model here, that is finding the different Reynolds stresses after you have a solution with K and epsilon. Fairly messy model, but possible. The production term, and here also the Coriolis force term, they will be okay to handle. They are depending on the unknowns already, so they are not any problems actually. Some trick here is some redistribution term that has to be modeled taking the wall into account, and they can be quite complex. So here is a model for handling this wall turbulent dependency. Quite messy actually. If we look at some of the results, then I believe the case for case A, that is without case B is without rotation, I think, and A, that is the positive rotation, wasn't it? Should be listed somewhere. Here we are. The upper A and the C parts, they correspond to negative rotation and then positive rotation. Negative rotation, part A, what does that mean? Negative rotation, well, the positive rotation, that is counterclockwise, so negative, that's going the other way around. So rotating it in the clockwise, then you will have a high pressure on this side, low pressure down here. Then the bottom wall will tend towards laminar flow. So that should be the part A. So here, tending more and more towards a laminar flow down here. Neutral, no rotation, and here you increase the turbulence. You have a pressure side down here. So the ASM can handle the different problems here with rotation, without rotation, and get quite clearly different results. The K epsilon, he won't really see the difference or the effect of rotation at all. So I'm not sure if he has compared them here. Has he? No. No. Oh, he just shows the results directly from with using the ASM, But I mean, the results from the K epsilon alone would be rather silly here. You won't even see the effect of the rotational numbers at all. The other way. Another problem, you have a small jet entering down here in the corner in a reservoir. So then you will have a wall jet alongside here, and then some outlet up here. You will then have one big recirculation zone here, one big vortex. The problem here will be resolving the jet entering here. And here they play around with K epsilon, and they play around with here a full Reynolds stress model. As you see, quite complex. The production term, no modeling needed. The diffusion terms, he needs modeling. The viscous term here, normally that one is included into the epsilon. Here the redistribution terms that can take energy from one of the Reynolds stress and give it to some of the others. And then you have a whole bunch of different wall models as well. And that's sort of the focus on this article. And as you see, they can be quite complex. For the mean result, the streamline, not a problem to achieve this one. With actually quite simple turbulence model, you will get that one fairly easy. But if you look into the details, then you will clearly get some differences. So here they are playing around here with how fast this jet is growing when it follows the bottom wall. They have compared here with some experiments done by some guys in Göteborg, I think. And then the full Reynolds stress model, and then compared with the K epsilon. So not totally stupid, but at least here you see the K epsilon is rather way off, while the full Reynolds stress model follows the experiments much better. So CF being then the skin friction coefficient alongside the bottom wall. Yeah, some other comparisons. K epsilon actually not so totally bad, but a little bit off. So looking into more complex turbulent quantities, the shear stress and the normal stress, then of course you can't actually use K epsilon. They don't have these different components of the Reynolds stresses at all. Then you have to use either ASM or, as here, a full Reynolds stress model to find them. Very hard to measure, so the measurements might be a little bit questionable here. They are quite complex to measure correctly, but he's done a fairly decent job actually. Yeah, we can have a peek on the last one as well. That's a plain cuvette flow. So the problem there is quite neat. The top wall is moving with a constant velocity. You keep the bottom wall fixed. No pressure gradient, no gravity. The driving force is friction. And the laminar solution, that's a straight line. The turbulent solution will be this S-shaped velocity profile. So here you know the Reynolds number before you begin. You know the average velocity. It will be 1/2 of the wall velocity. So cuvette flow, that's fairly okay to find or to set up as a problem for meaning you know the Reynolds number before you begin. The other classical problem, a Poiseuille problem, both walls are standing still and you add a pressure gradient. Then you have no idea what the Reynolds number is going to be. That's part of the solution. But what you do know then that is the forces acting on the wall. That you know before you begin with a Poiseuille. Here it's the opposite. You know the solution, the average velocity. You don't know the gradient for the velocity towards the walls, meaning you don't know the friction forces acting on the wall before you have the solution. Here it's possible to rewrite your equations to something like this as a steady state turbulent flow. So you still have, of course, this Reynolds stress that is unknown, but this is as far as you get with pen and paper. But you can use this as a test if this, say the sum of the viscous stress together with the turbulent stress, they have to be constant from wall to wall. So then you should get a straight line if you plot the sum of these two together. So that's a good final test. So here they have done a full Reynolds stress model. Everything as normal. Production term is analytically correct. You don't need to model that one. You need the dissipation. Here redistribution and diffusion. And here they have another dissipation term as well, as a sort of a why they have kept that one alone. Well, people tend to play around with the different terms into the diffusion terms. Some you might call this one a dissipation since it has viscosity in front, but that's your choice. Different models then. Diffusion, always a gradient in front, always a derivative in front of whatever is inside. That's a diffusion term. So meaning if you take a volume integral, you have only to concern yourself with fluxes in and out. So means you can reorganize these quantities inside a domain but not outside. The redistribution terms, pressure strain terms, here modeled quite complex. You have some special wall versions of them. And then of course it's a question, what's the distance to a wall when you have two of them? So here they have played around with a wall proximity function, f, to say the distance varies something like this, just to see the effect. Yeah, I won't go through the details in the models, just look at some of the results. Mean velocity profile, that is fairly easy to achieve. And here they have also compared with the DNS, and also I think they have some experiments, if I recall correctly. Here they have compared the circles. They are taken from a DNS that I did, and the straight lines, yes, that's their model. And for this one, there you have the turbulent shear stress. That's this one. And then you have the laminar, you might say, the ordinary viscous stress. And when you add these two together, you should get 1. So this line, that's calculated. It's not just drawn a straight line up there. So that's just to verify that you have a good solution. So the sum of these two is indeed 1 from wall to wall, as they should be. And the result agrees fairly well with the DNS. When you look into the detail of the different Reynolds stresses, then you see some differences. Here, the circles are the DNS, and the straight line will be the RSM, the full Reynolds stress model. If you had done this with a K epsilon, you don't have these three at all. You just have the sum of them being one single K. That's all you have. So he doesn't see any differences in direction. And for this flow, although very simple geometrically, you clearly have an inhomogeneous type of turbulent distribution. It's much more turbulent activity close to the walls. You have some turbulent structures alongside in the streamwise direction. Totally different when you go in the opposite direction or between wall to wall. And K epsilon, K omega, they can't see that at all. So they don't have these differences whatsoever. So to get a correct result, you clearly need quite advanced turbulence model, even for such a simple problem as this. Yeah, compared also with some experiments, and actually it's not so bad. Yeah, I won't go through all the details here. It's just a lot of different comparisons here, and it's very tricky to do some good measurements for a cuvette flow. How can you do that one in the lab? You need a moving wall. How can you get a moving wall without getting too much noise into your flow? Not easy to do it. I think they frequently, at least, they take a box, put on a wheel, and then they remove the front and bottom, and then they let the box move alongside the floor. Also, they have been using some elastic belt that goes around 2 cylinders. Then you'll have a cuvette flow in the center. But then the belt will start waving a little bit waggling, and then you destroy everything. It's very hard to do it experimentally, actually. Not easy to get very close to the different walls. So I think I will save the DNS for tomorrow. Also there we have to go through a little bit more turbulence theory when it comes to the law of the wall and stuff like that. But I think we'll do that tomorrow. Any questions from you? Then tomorrow, the rest of the turbulence, and also verification and validation. Then we stop here.